Hello, welcome to Empowered Learning. This video will be about differential equations and what that basic definition is, as well as classifications of differential equations. So this video is going to serve as sort of a introductory video to what differential equations is all about. And we're going to build upon this knowledge to be able to eventually start to study more types of differential equations and the techniques that we use to be able to solve them. So we will cover what is a differential equation, what is the difference in between an ODE, which that is going to be representative of an ordinary differential equation, versus a PDE, which is the acronym for a partial differential equation. We also want to talk about what is meant when we say the order of a differential equation, as well as what is the solution to it. We'll look at what initial value problems are, define that, and sort of get what the properties of an initial value problem would be like, so that we can recognize one when we see it. And lastly, we'll talk about what it means to have a general solution to an ODE, or ordinary differential equation, versus a particular solution to an ODE. So first, let's move into talking about the definition. So a differential equation is an equation involving a function, y is equal to f of x, that interests us, along with terms that may have derivatives of y. So in other words, you have an equation to where you have, let's say, either a function f of x, which is equal to y, or it's going to have some first or second or third derivative of y in it in some of the terms. So that's what that means. Where the solution to this equation is a function itself. And in this case, we're saying that y is the actual function. So let's say if we looked at an equation like this, 3x minus 8 is equal to 24. Okay. Of course, when we say we solve this equation, what we're actually doing is trying to solve for this variable x, and it's going to be a number. Well, in differential equations, what we see here, the actual function that we're looking for actually is acting as the variable in these equations. So that's really the difference in between a differential equation versus an other type of equation. The actual variables of the equations, whenever we're dealing with differential equations, are actually functions themselves. And again, they're characterized by having equations where you have terms where you're either going to have a first, second, third derivative, something like that, in at least one of the terms. Now, let's look at some examples here. So an example of what a differential equation would look like. So we see here for this first one, we see that we have a first derivative in the term on the left. What's on the right is just a linear term, and we're assuming that k is a constant, but it doesn't matter as long as we have at least one term in the equation, to where we have at a minimum a first derivative. That's all that's really needed. Of course, in the second equation here, we see that we have derivative of y with respect to x in this one term here. The rest of the terms don't have a derivative in it, but that's okay. As long as we have one term that has some type of derivative in it, that's all that's needed. Same deal here. We have second derivative and first derivative in two of the terms. So we know that that's a differential equation. Now, we contrast that with what we see here. We know that this particular equation from pre-calculus or college algebra is just going to be a quadratic equation. We know this is a linear equation. We know that we can consider this to be either an exponential or logarithmic equation. And of course, here, this would be what's called a rational equation, or a rational function type of equation. So what we're going to be dealing with are equations like these, and not necessarily these. Okay. We will have to solve equations like this in the process of actually solving differential equations. But the main idea here is trying to make sure that we recognize when we have a differential equation. And of course, we're going to learn various techniques throughout all the videos I'm going to make about this particular subject on how to solve certain types. All right, so what is an ordinary versus a partial differential equation? So a differential equation that involves some function y where y is a function of only one variable is what an ordinary differential equation is. Okay. So of course, if we say ordinary differential equation is basically a DE where y is a function of only one variable, then of course a partial differential equation is going to be a differential equation that involves some function y where y is a function of more than one variable. Okay. Or you could say two or more. So some of you may not have learned about partial differential equations, partial derivatives yet, and that's fine. Just kind of know that whenever you take a partial derivative of a particular two or more variable function, you take the derivative of that particular expression, I should say, where every variable that's not the one that you're taking the derivative of, you treat it as a constant. So for instance, just to make this easy, let's say y is equal to 3 times x times y. Okay. So if I wanted to take the derivative, the partial derivative, let me write that a little better here. So let's say we want to take the partial derivative of y. And let me fix this too, because I want to make this a different variable here. So let's say I have z there. So let's say I want to take the partial derivative of y with respect to z. Then I would ignore x, treat it as a constant. So that means 3nx would be a constant. And of course, the derivative of z with respect to z is just 1. Okay. Now, if I wanted to take the derivative of y with respect to x, then in this case, the z would be a constant. So 3 and z are constants. And then, of course, the derivative of x with respect to x is just 1. So that's what that would be. So when we talk about partial derivatives, that's what we mean. So coming back here. So for example, if we had this particular equation here, we see that since we have a partial derivative of some function u that we don't know about, we're going to call this a partial differential equation here, where we understand that u is actually going to be defined as a function of both x and y. Okay. All right. So the order of a differential equation. So the order of a differential equation is just the order of the highest derivative explicitly appearing in the equation. Okay. So as an example, we see that all of these examples here are examples of what we call first order differential equations, where the highest derivative of any term in the equation is a 1. For second order differential equations, of course, the highest derivative that we see would be the second derivative. Okay. And of course, third order, the highest would be third derivative. And as long as you have at least one term that has a derivative of highest order in it, that's all you need to be able to do to classify it. Now, if we take this equation, notice that this is what's considered to be a 6th order differential equation, not an 11th order. And so notice here that we have the second derivative of some function raised to the 11th power. That's not the same as having the 6th derivative of something, or in this case, having the 11th derivative of something. Okay. So we're strictly going by what is the highest order of derivative that we have. So now let's talk about the solution of a differential equation. If you can take some function y and you know it and you know what it is explicitly, and you substitute it into a differential equation, and on top of that, both sides of the equation come out to be the same thing for the interval values, let's say x values, when we say that the explicit function y is a blank to our differential equation. Okay. And so in this case, we're going to say it is a solution. So basically what I'm saying here is that if we have some function y, we plug it into our equation, and let's say on our equation, what we get on the left side is the same exact thing that we get on the right side for all the x values that we consider plugging into that function y, which is some function of x that we don't know of right now. But if we had that explicitly stated, then we can call that a solution to the differential equation because the left side equals the right side. Okay. Now, another way that we can state this is to say that y satisfies the equation. So we plug in y, which is some function of x, into each term where we can apply it. Let's say if we have to take the first or second derivative of it, apply all that, do it, and we see that both sides are equal, then we can also say that the equation is satisfied by that function y. Now, as an example here, let's consider this second order differential equation. And so here we want to consider this equation, and note that we could also express it in this prime notation. And we know that it follows that this particular function here would be a solution to this particular equation. Okay. Now, you're asking, how do we get that? Well, we just guessed. Okay. And we're guessing, and we're going to verify that our guess is valid. So to do this, we know that in this first term, I would have to take the second derivative of whatever this function is. In this term, I would have to take the first derivative, and then I would have to plug in what this actual function is here and see, does the left side equal the right side? Well, if this is our original function, then of course, the derivative of 2e raised to the negative x is just negative 2e raised to the negative x. And then if we take the derivative of the derivative, we get 2 times e raised to the negative x. Okay. And so here, what we go ahead and do, and I just kind of made life easy for myself, and I wrote this in prime notation down here. We just go ahead and substitute in everything. So the second derivative we know is this, is here. We know the first derivative, which is negative 2 e raised to the negative x, is here. And then we say 2 times what the original function is here. And we do all the math of that, and we see that indeed it does check out to where the left-hand side and the right-hand side of the equations are equal. And we know that for our function y is equal to 2e raised to the negative x, this is true for all x values that are in the real numbers. Okay, so we know that this particular equation is valid, meaning that y is equals to 2e raised to the negative x satisfies or is a solution to this particular differential equation for all values of x that are in the real numbers. So now that we see an example of taking a function and sort of guessing to say, hey, is this particular function going to be a solution to the differential equation? And we check it out and we say, yeah. This brings something up very important. And we want to talk about the fact of knowing, hey, what x values is that particular equation going to be valid for? Okay. And it's one of the things that in the whole process of solving differential equations that sort of kind of gets lost in the sauce, as I would like to say, because you're so worried about just getting what the actual function is. But it is also important to know what values of x you're going to use once you find out what that solution or a function to that differential equation is going to be. Because inevitably the whole point of solving differential equations is to come up with a function that you can use. So why find what you can use when you don't know how to use it? And I hope you get my point there. So one of the reasons why learning how to solve ordinary differential equations and partial differential equations is important is because, of course, we use them to model systems and or phenomena in our environment. Okay. And so part of the reason why we want to be able to solve these differential equations and know what values of x or t or whatever it is that we're going to use it for is that we're actually trying to model something so that we can predict some kind of phenomena or action that's happening. And so what I've done here is listed some examples of some of the things that it's real popular for modeling, I guess, applications that we model in terms of differential equations. So, of course, probably the two most popular are population growth and radioactive decay. And so if you remember from pre-cal here, we know that anytime we have the derivative of some function being proportional to itself, it is taking on the role of a function like this, some constant times e raised to the t, okay? And so, of course, you see that here where the a and the p sub 0 would be the same. And, of course, there is k here, which is going to be your, in this case, growth constant. For radioactive decay, same kind of equation. It's just that now our k is negative, and that would be our decay constant. If we were to try to model the spread of a disease, then, of course, this would be a differential equation that we could look at. And if we had defined y as being n plus 1 minus x, and that's so because we would look at the number of people who are already infected plus the number of people who are not infected would be n plus 1, where n is the number of people in a given population. And so what we're assuming here is that if we added another person to the population to try to see the growth of the spread of that disease, how would all that relate to each other? And of course, if we take this equation and solve it for y, we end up with n plus 1 minus x. So that's how we get that. And so, of course, here, the spread of the disease, since the number of people that are getting the disease, we expect it to increase. This constant here would be a growth constant. Thus, it would be greater than 0. We can also use this for chemical reactions, where, of course, this x here is going to be the amount of a substance that we call A remaining at some particular time, and B here is going to be, I guess, another substance that hasn't decomposed yet. Okay. So my point here is, of course, I have a few more examples. We got series circuits, and so I threw this in here because my background is in electrical engineering. So to find the voltage around a circuit loop, as we call it, we know that the voltage across an inductor is L di dt. The voltage across a resistor is current, which we call I times the resistor. And of course, current across a capacitor would be Q, which is going to be the charge of the capacitor, or let's say the polarization of the electrons, divided by the capacitance. And that's what that C is. And so, of course, if we take all that, of course, Kirchoff's voltage law basically says that the sum of all the voltages around a loop is equal to 0. So if we take all these relationships and add them together here, we see that we'll have a second order differential equation that we can use to model this particular circuit. Okay. Also have another one, draining a tank. And so this one follows Torricelli's law. Basically says that, hey, if we take some kind of fluid and we try to make it go through a small hole, there's going to be some sort of friction that's involved, just because you got so much of a thing trying to get into a little bit of space. Okay. Now, my point here is to just make that we use differential equations to model a lot of things in our environment. And so that's the main point of showing this. If you're following me throughout all these videos I'm going to do for differential equations, you're going to see that I come back to this whenever we start to actually do some modeling. We'll have to sort of lay a foundation for some techniques for solving at least first order differential equations first before we do that. But after we do it, we'll have enough knowledge to be able to actually go in and use some of these techniques to be able to do some modeling. All right, so the reason why knowing what interval of values your differential equation and the solution function for it is important is that in the context of what your differential equation is modeling, some values of x may not make sense to use, okay? So for instance, if I'm talking about modeling how a pendulum swings back and forth, I'm going to start at time as my independent variable, being time that's 0 or higher. I'm not going to look at the pendulum and say, hey, at negative 100 seconds ago, what was it doing? Okay. We're going to start with saying, hey, at time t equals 0, pendulum starts to swing back and forth, and we're going to model what that looks like from there. And so that's a simple example of what we mean when we say, hey, we want to make sure that essentially the domain of the solution to the differential equation, we actually have values of x that make sense. All right, so moving on here, let's talk about initial value problems now and general versus particular solutions. So note that a differential equation whose solution is a function, say y is equal function of x, this function may be a general solution. That is to say the solution is really a family of functions versus being a specific solution. So for example here, we see that this particular function, because it has this arbitrary constant in it, is what we're going to refer to as a general solution. Whereas for this particular equation, we see that c is actually substituted for an actual value, and we call this a specific solution, okay? And another way to say specific solution would be a particular solution, okay? Now, the reason why we say that a general solution has these arbitrary constants in it is because these constants can be anything, okay? If I was to let c equal 2, and then I say, what is the derivative of y with respect to x? Well, still going to be the same. It's going to be negative 2 e to the negative x plus 3, okay? And this is going to be the derivative of it regardless of if c is equal to 2 or c is equal to 3/4 or c is equal to negative pi or whatever. Really doesn't matter, okay? So here to kind of summarize here, a specific function that is a solution to a differential equation is better known as a particular solution to the differential equation. Now, in initial value problems, the particular solution is usually found by specifying certain characteristics about the actual function, y equals f of x. We may be given information about a point on the graph of the function or information about the first, second, or nth derivative of the actual function. So in other words, in order for us to do initial value problems, we are going to have to know something else about that function, okay? If it's a first order differential equation, we're going to have to know something about a point that's on this graph. If we have a second order differential equation, then we're going to have to know something about a point on this graph and the derivative of that function at that particular point, okay? Now, in a first year calculus course, you normally learn about how to solve these initial value problems when learning initially how to find the antiderivative of a function, okay? So in your first year calculus courses, when you learn about antiderivatives, you naturally go into, let's say, doing problems where you have something like, hey, here's a particle like the one I'm going to do for you here, and we know something about the acceleration of the particle, and we want to get back to what the position function would be based upon the acceleration, okay? And so I'll show you this example here quickly so that you can kind of get an idea of what this looked like back in your first year calculus course. So we have a particle moving with the given data below. And of course, that data here is just that we have this particular equation. And we know from this equation here, we have this information about the actual position function that we're trying to find. Now, note that we know that acceleration is the second derivative of a displacement or a position function, okay? And we also know that velocity is going to be the first derivative of a position function. And so the direct antiderivative of acceleration is velocity, and the direct antiderivative of velocity is position or displacement. Okay, so again, saying all that to say that we need to know this information to be able to do this problem. Now, the reason why acceleration equals to 10 sine of t plus 3 cosine t is a differential equation is because we know that we could represent acceleration as the second derivative of position. Okay, and so once we see that, then we see here that yes, this essentially is a second order differential equation. And if I can find out what my position function is, the most general position function, then I could use these two pieces of information here to find these specific position function out of all the ones that's possible. Right? Now, I'm not going to bore you with the details here, but we see that if I was to take the antiderivative of acceleration, we would get the velocity, which would also be the first derivative of position. And so in doing that, here you can't see it, but there is a constant that's here. So I'm going to put plus c here. And so that lets us know that when we take the antiderivative, there is an integration constant involved that we got to have. Now, what we need to do now is say, well, what is the position function? Well, we got to go down. We got to do the antiderivative again. And so we're going to take the antiderivative of velocity, which is just going to be the antiderivative of what we had up here. Okay. And of course, when we take the antiderivative of each term, we see that we have another integration constant that we have to deal with. And so now we see that our position function, or the most general position function, has two arbitrary constants in it. And we could use this information about the position and the velocity, or the derivative of position, to be able to figure out what both c and d are. And so now we'll do that. So if we take this position function and let t equal 0 and set it equal to 0, we see that once we do all that, we end up with -3 plus d is equal to 0, which means d is equal to 3. So we know what this particular arbitrary constant is now. We also see that if we were to take the first derivative of this particular function, which is essentially just your velocity function here, if we took that and let t equal 2 pi and set it equal to 12, then we see that the result of that ends up being c is equal to 22. So from that, we see that c is equal to 22, d is equal to 3, and this is our specific or particular solution to this second order differential equation that we're asked to solve. Now, one of the things that I want to note here is that in general, whenever we're talking about nth order ODEs or PDEs with initial conditions, and so nth could just be third, fourth, fifth, sixth, whatever, okay? We're just trying to talk about this in general. So the main thing here to know is that with these initial value problems, we're going to have exactly n values being assigned in these problems, and they're going to look like y of some number, y prime of that same number, and it keeps on going all the way until we get to one derivative short of what the highest derivative is. So if we go back to our problem here, notice that this was the second derivative of position was equal to 10 sine t plus 3 cosine t, and notice that we had everything up to the first derivative in initial conditions. Now, for here, do notice that these two x values are different, and that is okay. You do have instances where you can do that. I know in most differential equations courses, they try to keep it to where whatever x value you have here for, let's say, the original function will be the same x value that you're looking at with the first derivative, or whatever. But in general, you can have these x values be different. The main thing is that whatever your actual function is that you're trying to find out what its specific or particular solution is, you just have to know something about it. okay? And it's convenient to be able to know at a single point, in this case, what is the position and the velocity, but you may not be able to know that. So in this problem, we knew what the initial position was, but we also knew the velocity at 2 pi seconds later, okay? That's what we knew, so that's what we used, okay? All right, so again, the main point here is just to know that if you have a second order differential equation, you're going to have your original function and first derivative. You should have that information. And these values x of o could be the same or they could not be the same, okay? If it was a third order, then of course we would have original function, first derivative, and second. Now, also note that our solution to our initial value ordinary or partial differential equations satisfy these equations as well as the initial conditions. If a given function f of x satisfies either the ODE or partial differential equation, if you're dealing with that, or the initial conditions, but not both, then we know that the function is not going to be a solution to the initial value problem, okay? So in other words, let's say if I had some equation, a differential equation, and I know that my function y is equal to f of x, it's going to be that. But let's say one of those initial conditions that I have here isn't true, okay? Well, if one of the initial conditions that I have here isn't true, then it's not going to satisfy the equation. So that's basically what it's saying. So we have to know something about the particular solution that we're trying to find, even though we may not know explicitly what it is in total detail. We have to know something about it to be able to give us an inkling of being able to get to an answer with these differential equations. All right, so now we'll do a host of examples here to try to give you some practice on not only being able to do problems like the one I just did for you, but also ones where if we're saying, hey, here's this function, verify it's going to be a solution to the differential equation. So the examples that I'm going to do are basically going to be problems like that. So we want to find out what f of t is for this particular differential equation, and we see that it is of second order because the highest derivative is 2, the second derivative. And notice that we have 2 initial conditions, okay? So second order differential equation means 2 initial conditions. And in this case, notice that we don't have the traditional f of x of 0 and f prime of x of 0, okay? And again, I did this on purpose to show you that if we have more information about the actual original function than we do, let's say just one piece for the derivative and one piece for the original function, we could use that as well, okay? All right, so first thing we need to do is I'm just going to rewrite this as f prime is equal to 2e to the t plus 3 sine of t. Now, if I take the first derivative, not take the first derivative, but if we go down to the first derivative, we'll be doing the antiderivative of 2e to the t, which that's just going to be 2e to the t. The antiderivative of 3 sine t, we know that 3 is a constant, so we just ignore that. And the antiderivative of sine is minus cosine. And so here, and we'll say plus c for that. So this will be 2e to the t minus 3 cosine of t plus c. And so now to get to the original function, and just for clarity here, I'm going to go ahead and put the variable t in there. We need to take the antiderivative of what we see here. Of course, the first term will just be 2e raised to the t again, have a constant minus 3, and then the antiderivative of cosine is sine. Now for the constant, we know that the antiderivative of any constant is just going to be that constant times our independent variable, which is t. Because if you think about it, this is like c times 1, and we know that the antiderivative of 1 is just going to be whatever the independent variable is, okay? And then once we're done dealing with all three terms, we just do a plus d to give the arbitrary constant for that. So now this is our most general solution to our second order differential equation. To use our initial conditions now, we first let f of 0 equal 0, and that implies that everywhere where we see t, we're going to allow that to be 0. And we're going to have that equal 0. So that's going to make this whole term go to 0, that whole term go to 0. E raised to the 0 is 1. So what we essentially have here is 2 first term minus 0 plus 0 plus d, and that is equal to 0. And here we can easily see that d ends up being -2 in this instance. So now that we know what d is, we could take that information and use it to help us be able to find out what c is. So next we have that f of pi is equal to 0. And I'm going to clean up this equal sign here. So again, same function, but this time everywhere where I see t, I'm going to let it be pi. And that should be a minus, not a plus. So here, minus 3 sine of pi plus c of pi plus d, which is a -2. And just go ahead and just write -2 there. And that's going to equal 0. And so now from there, we know that sine of pi is 0. So this whole term goes to 0. We don't know what c is because that's what we're trying to solve for, but we know it's going to be pi times that. So here we could say 2e raised to the pi minus 2 is going to be equal to c times pi. And then, of course, from there, if we divide both sides by pi, I'll just do it here, then we eventually just get 2e raised to the pi minus 2 divided by pi, and that will be equal to c. And so that would be what our other arbitrary constant ends up being. I know it's not the prettiest thing, but it is what it is. So our final answer will just end up being the 2e raised to the t minus 3 sine t plus, and then we'll write in all that stuff for what c represents, and then minus 2. And so this ends up being our final answer for this particular problem. And so before we go on to the next example, I just want to make sure that you're thinking about this as well, is that now that we know what the original function was that was related to this differential equation, notice that we can plug in values of t that are any real number into here. So unless we have some context on whatever application this differential equation came from, we can assume that we can plug in any value of t that is a real number into it, because each one of these terms that has a t in it can accept any real number, and the term will turn out to be a real number when we evaluate it. All right, so I think one thing I forgot here is whenever I did this step, this should be minus like that, which means this should be minus like this. So I forgot those negatives there, so I need to go ahead and put those in. So this would actually be the actual answer. We could also change this and move the negative that's here to the numerator. And if we actually did that, then of course these two terms would switch around here. And we would have instead, get my pen writing here, this would be 2 minus 2e raised to the pi. So it could look like that as well if you want to make it look clean. Okay, so for the next couple of examples, what we're going to be doing is basically taking a ordinary differential equation and taking a suggestion to say, hey, is this function going to be a solution to it? We're going to find the corresponding derivatives for it, sub everything in, and see if it actually satisfies the equation or not. So we're going to do that, and then we'll also identify the interval of interest, meaning the x values for which that solution would be valid. So we see that we have a second order differential equation here. So we know that if we're guessing, or I guess we want to verify that y equals to e raised to 3x is a solution, first thing we may want to do is find out what the first and second derivatives are. Okay, so the first derivative of e raised to the 3x, using the chain rule, just be e raised to the 3x times derivative of the inside function, which is 3. So it'll just be this. Second derivative will just be derivative of the derivative. And if we repeat that process again, we'll get 9e raised to the 3x. And so here we could look at this as y double prime, look at that as y prime. So therefore here we can have y double prime minus 6y prime plus 9y is equal to 0. And that implies here, second derivative, 9e raised to the 3x minus 6 times first derivative, 3 times e raised to the 3x, and then plus 9 times e raised to the 3x, and that equals 0. So if we keep going here, we'll see that we'll get 9e raised to the 3x minus 18e raised to the 3x plus 9e raised to the 3x equals 0. And of course, 9 plus 9 is 18. So that means that 9e raised to the 3x plus itself is going to be 18e raised to the 3x. And so all three of these terms end up canceling each other to 0. So we see that, yes, our y equals to e raised to 3x does satisfy this particular second order differential equation. Now, we want to see, will y equals to x times e raised to the 3x, will that also satisfy this particular differential equation? Now, before we start doing this particular problem, I do want to say that some of you may be assuming that just because this one actually worked, then that means that this one should not work. And in the world of differential equations, that is not necessarily true. We could have a set of different type of functions that can actually satisfy the same differential equations, okay, or same differential equation. So I don't want you to think that just because we found an answer that that's going to be the only answer, okay? All right, so let's do this again. So here I'm going to use same equation. So that's going to be y double prime minus 6y plus 9y equals 0. And what we need to do here is find out the first and second derivative of this particular function here. So I'm going to go ahead and take care of that now. So for the first derivative, of course, we'll use the product rule here. So we'll take derivative of the first, which will just be x times e raised to the 3x plus x times derivative of the second. And the derivative of x is just 1, and 1 times e to the 3x is just e to the 3x. And the derivative of e raised to the 3x is just 3e raised to the 3x. So we see that here for the first derivative, we would just have e raised to the 3x plus 3x e raised to the 3x. Now for the second derivative, we take the derivative of the first derivative. Okay, and do some separation here. So second derivative, go ahead and take that. So the derivative of e raised to the 3x is just 3e raised to the 3x. And plus, got a constant 3. And then, of course, the derivative of x e raised to the 3x, we just got through finding out. It's just e raised to the 3x plus 3x e raised to the 3x. And, of course, we'll go ahead and simplify that. So we got e raised to the 3x here, plus another e raised to the 3x there, which is 6e raised to the 3x. And then we have 3 times 3, which is 9x e raised to the 3x. So now that we know what the first and second derivatives are, we can actually go in and substitute them into our equation, see if it's going to satisfy. So for the second derivative, we know that it's going to be 6e raised to the 3x plus 9x e raised to the 3x. And then next will be minus 6 times the first derivative, which will be e raised to the 3x plus 3x e raised to the 3x. And then we'll have, I'm going to slide down here, plus 9 times the original function, which is x e raised to the 3x. And all that is equal to 0. So we'll go ahead and distribute here. And I'm just going to get through writing all that down. And so now we can see that this 6e raised to the 3x cancels with this minus 6e raised to the 3x. We have this 9x e raised to the 3x plus another 9x e raised to the 3x add up to be 18. So these two will cancel with this third. And again, we see that this function, even though it looks different than the other function that we had up here, they both still satisfy the same differential equation. So that's part of the reason why we did this example, to show you that, hey, differential equations do not necessarily have unique solutions. Okay, so the next example, using the same differential equation here, we see that we have y of x is equal to 7e raised to the 3x minus 4x e raised to the 3x. And so for this one, I've already worked out. So since you kind of have an idea of how this works from the previous example, I'll just kind of talk through this one. So we see here that we need to first take the first and second derivatives of both of these functions. And of course, you see that I have done that here. So of course, our first derivative ends up being 17e raised to the 3x minus 12x e raised to the 3x. And then if we do the same thing again, take the derivative of the derivative, we get this 51 e to the 3x minus 12 e to the x minus 36x. And of course, here I could have, combined these together to make, one simple term and make it 39 e raised to the 3x. But I just decided to keep it that way. So we go and substitute everything in. So we got our second derivative which is represented by all of this, minus 6 times our first derivative, and then plus 9 times the actual function itself, and this should be 3x here, even though we can't see it. And then, of course, we'll distribute here and distribute here, which is done here. And from that point, all terms with e to the 3x in it, we combine like terms. All terms with x e raised to the 3x in it, we combine like terms. And so for here, we see that in this case, we end up having, again, all this adds up to be 0 because we got minus 114 plus 114. Of course, the minus 36 plus 72 minus 36 ends up being 0 as well. So all this ends up being 0. And of course, we knew that what we were trying to do is to say, does all of this end up equaling 0 to begin with? So we see that although this particular equation, well, our function here kind of looks like one that, hey, it may not work, we see that it does. And of course, later on, when we start to study second order differential equations in detail, you'll actually see why all 3 of these actually worked, okay? All right, so on to our next example. We have a different second order differential equation now. And remember that this is second order because the highest derivative in your terms that we see here is a second derivative. And so what we want to do here is figure out, is this particular function going to be a solution for it? Well, to do that, of course, we need to be able to take the first and second derivatives, see if it's going to work. So the first derivative of sine of 2x is just going to be 2 cosine of 2x. And of course, the second derivative will end up being a negative 2. And then, of course, we'll have another 2 here. And then this will be sine of 2x. And of course, all that just comes from the chain rule. We know that we ignore the constant 2 here. We know that the derivative of cosine is minus sine. And then, of course, the derivative of the inside function from the chain rule is 2. So that's why it looks that way. And we see here that our second derivative is just negative 4 sine 2x. And so we could rewrite this as y double prime plus 4y equals 12x. And we just substitute in. So for here, we are going to substitute in minus 4 sine of 2x plus 4 times y, and that's just going to be sine of 2x, and say that equals to 12x. Of course, these two terms here cancel to 0, and here we see that 0 is not going to be equal to 12x for all values of x, okay? So here, this particular function would not satisfy this differential equation here. And so, and now in this example, you're going to see why it's important to be able to know the domain or the set of x values for your actual proposed solution to see when it's actually valid. Now, if we look at 0 is equal to 12x, the only time that's going to be true is when x is 0. So that means that if I had a situation where I had y is equal to sine of 2x only when x is 0, then that particular function under the restricted domain of x only being able to 0 would actually satisfy that differential equation. However, we know that in general, sine of 2x, we can plug in any real number in for x and it would work. So, and that's what we're trying to consider here. And that's why we're saying that, hey, this particular function is not going to satisfy this differential equation for all the values of x that it should be able to do it for, okay? And of course, in this case, it should be able to do it for all real numbers for x. So here, this would be a case where this would not work, okay? Meaning that this function would not be a solution to the differential equation. And notice again that the only time that it would be is when x is equal to 0. All right, so in talking about the x values for where a solution is valid, I wanted to jump back here for a second and actually talk about the x values for which the last three problems that we did are valid for. And so if you look at this particular problem, we have exponential functions in here. So we know in this case, x could actually be any real number. And of course, since our differential equation was satisfied by this, and that means that it would be satisfied for all real numbers as well. If we go back to this example here, same kind of thing. This function here, we can plug in any real number into it. We get out a real number. And since this was satisfied by it, it would also be that. And same deal here. Okay. All right, so moving on here is sine of 2x plus 3x going to be a solution to the differential equation that we just got through talking about, and I'll rewrite it. So it'll be the second derivative of y plus 4y is equal to 12x. We want to know, will this function satisfy it? Well, again, we'll have to find the first and second derivative. And so first derivative will be 2 cosine of 2x plus 3. And the second derivative will actually end up being negative 4 sine of 2x. And of course, the derivative of any constant is 0. So in this instance, we go ahead and substitute everything in. So this would be negative 4 sine of 2x plus 4 times y, which in this case would be sine of 2x plus 3x, and we set that equal to 12x. So here, if we did that, that would be negative 4 sine of 2x. We distribute the both terms here, plus 4 sine of 2x plus 12x equals 12x. These two terms cancel, and we see that 12x will equal 12x for any value of x within the real numbers. So yes, this particular equation or this particular function would satisfy our differential equation that we were given. Okay, so for our last function that we want to try in example number 3, again, we're using this differential equation, y double prime plus 4y is equal to 12x, and we want to see, does the function 3x satisfy it? And so here the first derivative of 3x would just be 3, and the second derivative would be 0. So of course, if we were to go in and substitute everything in, we'll see that this one will be relatively easy. Second derivative would be 0. 4 times the original function would be 3x, and that will be equal to 12x. So again, we have 12x is equal to 12x as long as x is any real number. So therefore, this is also a function that will satisfy this particular differential equation. So now we're going to close out with two other examples that were very similar to our example number 2, where what we wanted to do is find either a general solution or a specific or particular solution to a given differential equation. So what we want to do here is consider this differential equation that we're given. And what we want to do first is find a general solution to y of x, meaning that we basically want to find out what is going to be the most general solution to this ordinary differential equation here, okay? And noting that we could look at dy over dx is just y prime of x. Essentially, all we really need to do is take the antiderivative of the right side. So here I'll go ahead and rewrite this down. And of course, if we took the antiderivative on the left side, that would just give us the function y of x. And the antiderivative of 6x would be 6 times x squared divided by 2, using antiderivative rules. Same thing for next term, be 2 times x cubed divided by 3. And then we'll have an integration constant there. And of course, in simplifying everything, that will be 3x squared plus 2/3 x cubed plus some arbitrary integration constant c. So for part B, we want to find out what is going to be our constant of integration to make our general solution a particular or specific one if we know that when x is 0, y is 1 for our function y of x. And so if we look at that, and I'll actually do the work up here, we know that since we have y of x to be 3x squared plus 2/3 x cubed plus c, and that means that y of 0 is going to be 3 times x, or 0 raised to the 2 plus 2/3 0 cubed plus c equals 1. And both of these terms end up going to 0, so c just ends up being 1 in that case. So what we would know in this case then, that's of course c is equal to 1, and if we wanted to know what the actual function was as a result, even though the question doesn't ask for this, I'm just going to give this information anyway. Then what this would be is the particular solution for this differential equation given this piece of information about the actual solution. All right, so now we want to do the same thing, but we want to do it by letting x be 1 and y be 0. So same exact thing we did up here, but we're going to let x be 1, let y be 0. So in this case, we see that y of 1 is equal to 0. Let me switch that around. So y of 1 equals 0. That implies here that we have 3 times 1 squared plus 2/3 1 cubed plus c, and that's going to equal 0. And so now we just need to solve for c. First term would just be 3. Next term would just be 2/3. And that would be plus c equals 0. And of course, it's just simple arithmetic at this point. So 2 plus 2/3 will just end up being 11/3 plus c is equal to 0, which means c is minus 11/3. And of course, that's what c would be. And if we wanted to know what is the particular solution, it would just end up being what I'm writing here. Okay. And so again, the point here is to tell you that based upon what the initial condition is, that also tells us what our particular solution to our differential equation would end up being. Okay, so for our final example for this particular video, we want to verify that the function y of x equals to ax plus bx times natural log of absolute value of x is a solution to the following ODE that you see below. And of course, I've also written it in prime notation. For this one, it is a little long, so I went ahead and just wrote it out. It's not too long, but again, I think we kind of get the idea of what's going on here. The main point, or the main reason why I want to show this example, is because of the fact that notice that if this is a solution to this particular differential equation, it's only going to be valid for values of x that are all real numbers except for 0. Okay, and the reason for that is, if you look here on the left side, if I was to try to rewrite everything in terms of just having like a second derivative, something plus or minus first derivative, here I could divide both sides by x squared. Okay, so if I did that, that would be fine. But notice that this would only be valid, legal, and true if x was not equal to 0. Okay, and so it's these little things that we have to pay attention to based upon the type of differential equation that we're dealing with, to make sure that, hey, when we get this answer, it's got to make sense. Now, if we're verifying that this particular function here is going to be a solution to it, notice that if I tried to plug in 0 here, then my entire function would be undefined at that point, because of course we know natural log of 0 is undefined. Okay, so again, we see that the proposed solution here, its properties are also coinciding with the properties of the differential equation, to let you know that, hey, even if we got an answer for this, we know that we couldn't plug in an x value of 0 into it. Okay, and so we're going to verify that this particular function is a solution to this differential equation that we see here. And then afterwards, we're going to use the initial conditions here, that y of 1 is equal to 3, meaning when x is 1, y is 3. And when the derivative of y is evaluated at 1, it is equal to 8. So if we see here, the first thing that we need to do is take this particular function and we need to take the derivative of it. Okay, so of course, the derivative of constant times x is just that constant. We see that here, and we ignore the b and then take the derivative of x times natural log of x. And of course, x times natural log of x, we'll need to use the product rule to be able to do that. So we see the product rule is being used here. We clean up everything, and so we see that this is what the first derivative looks like. And again, this is valid as long as x is not equal to 0. And I didn't write this here, but I need to go ahead and put it. We're assuming here again that this is going to be absolute value of x there. Okay, if I just had the regular parenthesis, then I would only be able to say that x is greater than 0 at that point. But because I actually have the natural log part, natural log of absolute value of x as part of this particular function, we can also consider all negative values of x as well. All right, so now that we have that together, of course, we take the derivative of the derivative. And of course, taking the derivative of the first derivative is a lot easier to do. We just end up with b divided by x. But again, notice that here, since x is in the denominator, x is not allowed to be 0. So what we see here for the second derivative is valid as long as x is not equal to 0. And so now we just go ahead and substitute the second derivative and first derivative into our differential equation here. Okay. And so we see that when we do that, here's where the second derivative is substituted in. Here's where the first derivative is substituted in. And here's the original function. And again, don't know why I didn't do this, but this should be natural log of absolute value, natural log of absolute value. Okay. And so then, of course, in doing all this, we combine like terms, and we see that pretty much everything cancels out to 0 on the left side. Go ahead and put these in. And so because of that, we see that this particular function, ax plus bx times natural log of absolute value of x is actually a solution, general solution to this differential equation. Now, to find the specific or particular solution, we use our initial conditions. So, of course, now that we know that yx is equal to ax plus b sine of natural log of x is an actual solution to our differential equation, we let x be 1, y be 3, substitute everything, and we see that a ends up being 3. And when we consider the first derivative of this particular function here, and I think I left something out here. Yeah, there should be an x in there. I forgot to write that. And so now, of course, with the first derivative, remember we found the first derivative here to just be a plus b times natural log of absolute value of x plus 1. So we see all that. Substitute that in here. Let x be 1, y be 8. Do all the evaluation, and we see that b ends up being 5. And so we see here that, again, a was 1, b was 5, and here is our particular solution for our differential equation that we were given. And this particular solution here is valid as long as your values of x are not equal to 0.